This talk is going to be about, some aspects related to security and scalability of federated learning. It is joint work with several PhD students, former postdocs, and colleagues that I have listed here. All right, so probably for this group, federated learning doesn't need motivation. You are all interested about federated learning. Mostly, the way I see this is that there is going to be a surge of devices at the edge that collect data, and they want to be equipped with AI and machine learning. So the problem is, how would I enable distributed learning at a massive scale while ensuring privacy, security, and trust of the data that is collected and born at the edge of the network? And as we all know, a promising approach to this problem is federated learning, and that's why it has gained a lot of attention in the past couple of years. The main principle is simple. The idea is you would train locally, and then you would average and aggregate the models globally so that collectively these users can train and learn better and better models. So this way the data would stay locally at the users and won't be revealed to other users or the server for aggregation or for the training purposes. Although it is simple, what has turned out to be is that this problem has a lot of exciting challenges, a lot of exciting problems that I'm sure in your seminar series many people have talked about them. From our group and our perspective, we are interested in several aspects of this problem, all the way from foundations of algorithm design to scalability and trustworthiness. Just to highlight a little bit on the algorithm design, the common problems are: how would you do the model aggregation? When do you aggregate them? What would you aggregate? How are you gonna aggregate the models? Looking at data heterogeneity that creates non-IID distribution at the users to understand how to design the learning process across these heterogeneous sources of the data, looking at aspects of personalization, like what would be the loss metric for the training, as well as something that hasn't been explored much in federated learning, which is limited or maybe no labels at the users. On scalability, there are many issues. For example, these devices, you cannot train large models, although federated learning starts by assuming that you can locally train at each user, but typically you can do it. There is a lot of memory, compute constraint at the users, and you have to figure out new ways of enabling federated learning. Also, the aspects of convergence as you scale from maybe 1,000 users, that is the focus of today's machine learning, today's federated learning, to millions of users, and other aspects, which is what is the right model for this setting as opposed to generic models that have been developed under centralized learning scenarios. And finally, on trustworthiness, there are the issues of security and resiliency of model aggregation. What if you have active adversarial nodes, as well as there are opportunities that would arise. For example, you may have trusted environments that you can leverage at the server. So these are the problems in our group. We are doing a lot of work on those topics. And as it was mentioned at the beginning of the talk, we have a new center in collaboration with Amazon. It's called USC and Amazon Center on Secure and Trusted Machine Learning. We are doing a lot of works there. We have just launched this. As you can imagine, Amazon is like a enterprise that is interested in such technologies. And I think this alliance could help us understand better problems that could arise in this domain. If you are interested, you can visit our center and stay tuned for upcoming news there. But for the sake of today, there is a lot of material here. What I thought was I tell you a little bit about our works on secure and resilient model aggregation, as well as addressing the resource constraint at the edge nodes. So we may not have time to go through all of that. I try to, talk a little bit about some of the details, but we can go through at high level at parts to make sure we cover a variety of topics. In the meantime, it would be great if you make it interactive. If there are questions, feel free to ask them, makes it more interesting. Otherwise, I just see myself and I'm talking to myself. All right, so the first part, I'm gonna start by talking a little bit about model aggregation, in particular privacy and security concerns in federated learning. As we talked before, the first step is you are gonna train locally. In the second step, you want to aggregate the models. That would mean, let's XI denote the locally trained model of the users. You come up like a naive federated learning algorithm with a weighted averaging of those with weights PI to come up with the new model for the next iteration. One problem that arises here is that these locally trained models of the users, they cannot be revealed directly to the server. And the reason for it is what is called model inversion attack, meaning that although the data stays at each user, if you reveal the model, it is possible to invert it and learn the data set. So there are various attacks. This is like one by Fredrickson et al. That show that here is an image that you can reconstruct from a trained model, and here is an image in the data set. So you can reconstruct it to a good extent. That's why a key component of federated learning would be secure aggregation. And what it would mean is, how would I aggregate the models without learning the individual models? Okay. So it's kind of, you have n numbers, you want to know the average of them, but you don't need to know each one of them. How would you do that? This problem at a high level, looks similar to problems in multi-party computing, because in multi-party computing, your goal is also to do a computation without revealing the inputs, but there are some tweaks into it. And the first algorithm that was proposed for solving the secure aggregation was this nice paper by Bonawitz et al. At Google that proposed practical secure aggregation. So we are going to take a look at that to motivate some problems in this domain. So how do they do it? What is the idea? The first idea which existed in the crypto literature was to use additive masking. And what it would mean is that, let's look at the scenario that there are 3 users. The server wants to learn the sum of the models, XIs, and it should only learn the sum, but not the individual XI. The idea of additive masking is you add noises to these models so that the noises would cancel out when you add them up. For example, the noise at user 1 is Z1, at user 2 is Z2, and at user 3 is negative Z1, negative Z2. Now, what you can see is once the server has these 3 things, it won't learn any of the XIs individually because it is protected by the noises. But if the server adds them up, these noises would get canceled out and it would learn X1 plus X2 plus X3. So at surface, it seems simple. The challenge here is what is called the user dropout or delayed users, which is a common scenario in federated learning because it's going to be scalable across many users. Typically, these users are mobile users or light users like typical AI-assisted devices at home. And at times, although they may have trained locally something, but they won't be able to update the model in time or may not be participating in the aggregation phase because they may be busy with other things. So the question is how to deal with the user dropout. And as you can see in this toy example, if user 3 is dropped, then all of these things that are uploaded from user 1 and 2 would be useless. And the idea proposed in the paper that I mentioned was each pair of users would agree on a random seed, and they would use that for generating noises that they would use for protecting their models. So let's say for now, each user U and V would generate a pairwise random seed that only the 2 of them would know. And once they do that, each user U is going to upload its model by adding a lot of noises. And these noises have a specific structure. First of all, this part is a noise that is based on just a private random seed of user U. This would protect it, as I talk later about that. This other part is related to the pairwise random seeds that they have created. And the idea of this summation is that it mimics the additive structure that we discussed before. Because if you sum this across all the U's, you can see each term appears once in the positive, once in the negative, it would cancel out. Okay. So these parts is the idea is you are going to use the pairwise random seeds for creating additive mask. And this other part is for the self-protection of the users. Now, once you do that, each user is also going to secret share its seeds to other users in the network so that if he or she is dropped, the server can request the secret shares and reconstruct it. So let's see how that would work. Now, once each user is applying this protocol for adding the noises, they will upload the masked model to the server, and the server is going to have a set of users who have survived and set of users that have been dropped out, is going to sum up across all the servers, across all the users that are surviving users. The problem with that is you need to also cancel these noise terms from dropped out users. The way you would do it is, since they have secret shared it to other nodes, the server is going to reveal it to whoever who has survived and say, these are the list of dropout users. Can you tell me the secret shares of the random seeds so I can do the cancellation and subtract the corresponding noise terms? Meaning the noises in the surviving users would cancel out. The remaining ones, since it has been secret shared, the server is going to request it and manually cancel them out. Once it does that, the server are also going to say for the surviving users, you guys are in my list, reveal your private randomness so that I also cancel your private ones. This way, each user would either be included in the surviving users or the dropped out users, and it would either be protected by the pairwise seeds or the private seed. And all the noises would get canceled out. So it's a method that you use pairwise randomness for creating additive masks and use secret shares to take care of dropout users. That's how it is working. But let's see, how does it perform? We are going to look at the scalability aspect of this. Means that as the size of the network, there is going to be more and more users that you want to aggregate. We want to understand how complex this method is going to get. Here is an experimental evaluation of the scheme over Amazon EC2. On the x-axis is the number of users. On the y-axis is the total runtime. Here we are just focusing on one round of aggregation, the model size being 100,000 elements, each of them typical 32 bits entries. So it's a light model. There are 3 plots here. They correspond to how much dropout you have. The solid one is 50% dropout, dashed one 30%, dotted dashed is 10% dropout. There are 2 things that you would notice is as you are adding more and more users, the complexity grows quadratically. Another thing you would notice is that as the number of dropouts increases, this becomes much more heavy and much more complex for the server to get rid of the noises. The reason for quadratic is obvious because you are doing pairwise masking, and that grows quadratically. The reason for why, as there is more and more dropout, it has significant effect on how long it's going to take for the server to do the aggregation is because what I showed you here, this manual reconstruction and cancellation that is happening by the server. All right. So if you look at the breakdown of this algorithm, here is the same thing. This is the total runtime. If you look at that, you can see the bottleneck here is really the reconstruction at the server. Recovering for the random masks of the dropout users. There are so many users, so many pairwise seed that is going to be the bulk of the runtime and bulk of the bottleneck here. So when we look at that problem, the first question that came to our mind is that, is this quadratic complexity fundamental? Means that's the price you have to pay for enabling security, or can we overcome that? So the first result that I wanted to talk to you about is our algorithm called Turbo Aggregate. And in the same plot, I'm showing the performance of Turbo Aggregate. There are 3 versions of it. Don't worry about that. I will tell you later. Look at just the purple version, which is the best version. On the same plot where I'm plotting the total runtime versus number of users. As you can see with this method, first of all, you don't have quadratic growth anymore. It is linearly growing. And the second part is that you don't see the difference between 10% dropout, 30%, and 50%. All of them are lumped together. What is the magic here? The magic is using ideas from coded computing. That's a research area that we have been pushing for, as well as several others in the past few years, where the idea is you bring ideas from coding theory to distributed computing to avoid issues like stragglers, failures. And this is a prime example because the dropout users are examples of failures and stragglers in the system. And coding theory in general is a very powerful tool for dealing with failures in the system, as opposed to manual reconstruction and canceling out from secret shares. So that's the idea here. So what I plan to do, tell you a little bit about how Turbo Aggregate works, and then motivate some directions in this domain if you are interested on the security aspects of federated learning, which there are a lot of problems in that domain. Before I proceed and tell you on the technical side how Turbo Aggregate works, maybe if there are questions at a high level, you are welcome to ask.
There is one question by Konstantin. I'll try to unmute him. Yes, please go ahead, Konstantin.
Thank you. I have a couple of questions. So during deciding during negotiating this shift pairwise, as I understand, this common secret shift is known for both parties. So, and is it so?
Correct. This SUV, is it what you are referring to? This pairwise seats? Yes. It's like the typical method of agreeing on a, SUV over a public channel, so only users U and V know it, nobody else would know it.
Okay, but if a server, like if assume there are 2 users, U and V, and server, and if server and user V will collude, then they can jointly reveal message of user U.
Well, remember, it's not only protected by one SUV, it is protected by many other users, correct? So that will put the burden on the server, means that the server needs to collude with more and more to cancel out all the noises, because this is what user U is uploading. It's not just one other user V. It's like collectively they are protecting each other.
So I just want to check. So if in this schema, how? I mean, if are we in the setting when we trust to the server, or this also work
Very
when
good.
server?
Yeah, I should have said what is the security model here. Excellent. So the security model is honest but curious. Everybody, meaning that both the server as well as other users are honest but curious, as well as allowing 50% colluding, meaning that up to 50% of the users or users with the server could collude with each other. And you want to make sure, as long as they collude, the individual models are not leaked. So I had it here, maybe. That's a great question, actually, to be clear on the security model. The assumption here is that you will have up to 50% collusion in the system.
Okay, thank you.
Sure. Any other questions?
So it seems there are no other questions in chat.
Okay.
So just as a reminder, if you have a question, please post it to the chat or just use raised hand feature in the participants menu, and then we will unmute you. So please continue, Salman.
Sounds great. All right, so how does Turbo Aggregate work? There are 3 main components of it. The first part is that instead of using a star topology, like all the users to the server, we use maybe better aggregation topologies that are commonly used in distributed learning literature, for example, circular aggregation or tree topology that I will discuss later. So first, changing the aggregation topology. Another one is the same as before, which is masking local models with additive secret sharing. That's the same as before. The third part, which is the main new ingredient, is that as opposed to reconstruction by recovering the secret shares, our goal is to use redundancy in the aggregation system so that we can leverage coded computing for dealing with the user dropout or delayed users. So that's the key component.
Okay, sorry,
So
Salman, we have a question. I think
Sure.
Slavomy raised hand, so I'll unmute him.
Yes, I have a question related to Konstantin's question, that you mentioned that like the collision may be up to 50%.
Correct.
So this seems quite big to me. Like I would like assume that it would be maybe like 1/3, which is like this magic constant for the Byzantine index. Because like, do you also take into consideration that, for example, server may send different messages to different users? For example, he may send to the some users that different users disconnected, and to other users that they're still continuing, and so on.
Excellent question. As I mentioned, the model where the 50% comes is under honest but curious, means that the server and the users cannot deviate from the algorithm. But it doesn't mean they shouldn't, means that that's just the model. In reality, you can imagine they will become more adversarial setting, like Byzantine setting, and that's where I will mention some ideas and thoughts for future efforts. But for now, everybody is just following the protocol. We want to make sure they are not learning afterwards from what they have seen.
Okay, thank you.
Sure. All right, so as I mentioned, for the first part, we are going to use a circular aggregation. There is no magic there. The idea is that you are going to partition the users into groups of size log n, and there is going to be n divided by log n groups. The way the aggregation would work is you will pass, each user is going to pass the model to users in the next group. There is no need for having direct links between the users. I mean, everything here assume is over the internet, and all of this may go through the cloud, through the server, etc. So these parts, these links are just, higher level links between them that they can communicate with each other, so they can pass the model to the next group. Once they do it, every user tries to come up with the aggregate model of all users in the groups before it. For example, this user knowing the sum of blue as well as everybody before, the same. As you can see, there is already redundancy in the system, and that's what we want to leverage for tolerating potential dropouts in the previous group. But once they do it, they will pass it to the next group, so that at the very end, you will have the sum of all models in the system. Okay, so that's the circular aggregation. The other part is when you are passing the model to the next users, of course, you need to protect it because you don't want others in the system, not to other users in the network to learn about your model. That part, there is no special method here. We use, additive masking, the same as what I mentioned before. That would require pairwise agreement only between users in one group to the next. And remember, the group size is small, is log n. So the complexity of that would be log n squared. And there is n divided by log n of the groups. So if you multiply that, the complexity would be n log n as opposed to n squared. So that part is okay. You can create these additive masks and add them. The idea is that if everything works out and there is no dropout, these additive masks would cancel out at the end, and the server would be able to recover the sum, but nothing else. So that part is the same as before. And the same thing when a user is passing the aggregate model to the next group, it's also gonna protect it with additive mask. And you would be able to, if each user, for example, in group L+1, sums up all the aggregations that is getting from the users in the group before, if it sums them up, under no dropout, it would be able to recover the aggregate of everybody before that group. Now it comes to the main part. What if one user is getting dropout? So the user, for example, this user cannot get all the aggregation that would be needed from the users in the previous group. What would it do? And that's where we are going to apply coded computing. The idea of coded computing is if there is some data that there is computation done over it. For example, in this case, the computation is aggregation. You want to make sure that you protect yourself against dropout in the data. You would inject redundancy in your data so that after computations, the result of computations could be recovered. The method that we are using is called Lagrange coded computing, where the idea is, imagine these XITILs or, for example, the masked models that the user wants to pass to the next group. You pass a polynomial through them. The redundancy would be picking other points on that polynomial. If you want to know more about that, you can read our paper on Lagrange coded computing, but I'm not going to go to the details here. So once you do it, essentially each user in a group is going to add redundancy and pass also coded aggregates to the next users. So remember previously it was passing the aggregates. Now is also going to do coding and is passing coded aggregates. So it's passing double the number of models to the users in the next group. Now, the important part is that the user is going to add, apply coding to the aggregate models. And then the users in the next group, they're going to aggregate the coded versions. The key property that we want coding, aggregation, and masking commute so that the aggregation of the coded masks correspond to the coded version of the aggregation. After, if such a commuting would hold, essentially each user is getting several mask and coded version of it. The problem becomes the same as data reconstruction under erasures. Because you have some data and you have a coded version, you can potentially tolerate dropout in the data. All right, so how would that work? If I go back one slide. Remember, the goal here is for each user to recover all of the aggregates that are passed to him from the users in the previous group. But now what does it have? It has those SIs. These are like the aggregate models passed, as well as coded version of it, but potentially some of them are dropped. And that's where you apply polynomial reconstruction to figure out what are those dropped points. For example, if this red one, S1 tilde, is a dropout one, you would reconstruct it by having enough points on the polynomial. And exactly since we have double the number of points that we need, that's where we can tolerate for 50% dropout in the previous group. So let me explain all of that maybe through an example. Let's look at the scenario. There are three groups of size 3. The first users would start by having local models X1, X2, X3. At that point, they will add masks and they will pass it to the next group. There is no aggregation so far. Now users in the next group, for example, user 1 and 2, they receive the coded versions, right? From the previous group, they will recover the aggregate so far. For example, this is the aggregate that user 1 knows so far, and this is the other aggregate. It will apply the coding to both the aggregate version and create a coded version and pass it to the next group. Now, at this point, for example, if you look at the user 1 in group 3, it got 4 things because this user would drop out. It got the aggregate from this user and the coded version of it, the aggregate from second user and the coded version of it. The only missing thing is what was the aggregate that user 3 wanted to give me, but it got dropout. So you apply the decoding procedure that I mentioned to you. You will fill up what was the aggregate of user 3 in group 2. Then you can proceed and apply the aggregation and continue. So what it would require is extra coding at each user and decoding at each other user for the dropout users. That's the penalty that you're going to pay. So what is it that theoretically we can guarantee for this scheme? First of all, in terms of the complexity of it, as I mentioned to you before, the complexity of it is dominated by the secret sharing part. That is, you need log n squared times number of groups. That's where n log n would come to play. So that's the complexity of the system. In terms of the robustness, as long as you have less than 50% dropout, okay, so in this case, the dropout is probabilistic. Each user may be dropped with probability P. As long as P, the dropout probability is below half, the server can reconstruct the full aggregation model. So you have the same robustness guarantee as the scheme that I mentioned at the beginning. In terms of the privacy, what you can guarantee is that individual user models are protected as long as the number of adversaries is less than n divided by 2. And just to reemphasize again, these adversaries are honest but curious, and they can collude with each other. So as long as half of the users or together with the server that are colluding with each other are adversary, no individual models would be leaked. Just one clause here, if the server is leaking with the users, it may learn some of the partial aggregates between the groups. But again, the guarantee here is that the individual models won't be learned. Still, maybe you learn the sum of the aggregates in one group, which has size log n. As I mentioned to you, there are some higher level optimization that you can do. For example, there is a lot of parallelization opportunities. You don't need to wait for all other groups before you proceed. For example, the local models could be passed while waiting for the aggregates to arrive. So that part is straightforward. The other one is, circular aggregation is easier to illustrate, but there are better ones that make it parallelized. For example, hierarchical aggregation between the groups. For example, using a tree topology from group 1 to 2, 3 to 4, etc. These methods are typically much better practically. In terms of theoretical guarantees, there is no difference. And that's where, it comes to the experiments that I discussed to you before, those experiments over Amazon Cloud with just some small models and the dropout probability P. And that's where the 3 curves that I showed you before came from. The best one is based on using the tree topology for aggregation, the hierarchical aggregation. As you are seeing, again, there is no difference between the dropouts. That's the important part. The reason for it is there is no reconstruction afterwards that needs to be done. Each user individually is applying the decoding, and the system is already robust for up to 50% dropout. So it's kind of, you are paying a premium of coding a priori, and you build in robustness to 50% dropout already with it. So there is no extra cost that you need to pay as the number of dropout would increase. It just corresponds to a slightly more complicated decoding at each user. So let me also show you the breakdown. This is the breakdown that I showed you before. This is the breakdown of turbo aggregate. Here, the time that is spent is on encoding, decoding, and the communication. Maybe the important part is encoding and decoding are very light compared to the server reconstruction that was done in the Bonawitz scheme. In terms of the communication, they are on par with each other, means that there is no difference on communication. All right, so that's for turbo aggregate. Maybe let me spend a little bit time to tell you a little bit what could be beyond turbo aggregate. So this work, we did it like in more than a year ago. Since then, there has been other very interesting works in the domain of secure aggregation. One of them has been related to upgrading the scheme of Bonawitz that I mentioned to you to also break the quadratic barrier. And there is a very nice paper that shows it is possible. And the idea there is, don't use the fully connected topology, for creating the pairwise seeds and doing the aggregation to the server. Instead, apply a random topology with lower degree, and that one can also be used for breaking this quadratic barrier. So that's an alternative method. The other part is related to the communication size in both turbo aggregate as well as other aggregation protocols. One issue that we have here is that the size of the communication between the groups for us is going to be as L log n, where L is the model size, log n is the number of users. So the problem with this one is if you have many, many users, your total communication would get a multiplicative hit by log n. Okay, so you ideally want your communication to be just proportional to the model size, nothing extra. So if the number of users is small, log n, maybe you can avoid it, but if it is growing, that would be a penalty that you pay for turbo aggregate. The idea was there was another paper by Salman et al. Called fast seg aggregation that broke that barrier. And instead of L log n, they needed a communication complexity of L plus n. Okay, so it's kind of you add the additive part. And that is very appealing if you are aggregating very large models. Whether there is going to be large models at the users, that depends on the scenario. As I mentioned to you, often the users are resource constrained, so maybe you don't have that much of a large model at the users. But if L is something that you are worried about to get very large, then there are methods that you can also reduce that. So these are some of the recent things that have been done in the domain of secure aggregation, but still there are many other problems. One of them several of you asked about, which is so far we assumed you have honest but curious users, but you can imagine once federated learning is going to be applied at a larger scale, everybody using it, there is going to be all sorts of users and there is going to be malicious behavior. So the idea here is how to have defense against stronger attacks, in particular Byzantine attacks. In those cases, bad users may try to inject a bad model. And the problem is that in secure aggregation, you don't see the individual models. The server only aggregates them. So the question is, how can you detect adversarial models that are injected by the users without seeing the individual models? Okay, so it's kind of these two play at odds with each other. If the server, the aggregating server, can see the individual model, there are various methods that you can apply for outlier detection, whether performance-based outlier detection or distance-based outlier detection. But if we want the server not to see the individual model, just the aggregate model, how can you do that? In the case of distance-based outlier detection, we have shown it is possible. We have a paper called BREA, Byzantine Resilient Secure Federated Learning, available on arXiv, that shows at least for distance-based outlier detection, it is possible to detect outliers without seeing the individual models. The idea there is, essentially you are going to make the scheme from turbo aggregate a bit more complicated, where you would need some verifiable secret sharing of the local models from each user to other users in the system. Once you have that, then you can apply secure multi-party computing so that the computation of the distances between the models could be done across the users in the encrypted domain, so that you can figure out the outlier detection. Means that in this case, your computation is outlier detection. You can do it without seeing the individual models. And that's why for this class of algorithms, it is possible to do it, because outlier detection is formulated as calculating a distance, and the problem could be cast as secure multi-party computing. Your goal is to learn the distances without knowing the individual models. If you want to do performance-based, it is becoming much more complicated, because the computation for this performance is not something you can easily model it as a polynomial computation that you can deal with secure MPC. And that's where There is no work that address, performance-based outlier detection that are often more effective in the encrypted domain. All right, so let me skip the details of the BREA framework. Nevertheless, you would do secret sharing of the model between the users, and you do your outlier detection. And the guarantees that you can prove is you would be able to not tolerate active adversaries in the system. Let me show you some experiments on how such a scheme would work. In the context of adversarial schemes, there are many types of attacks that active adversaries can apply. Here we are looking at adding a Gaussian noise or flip of a label by the schemes, just to show how severe those attacks would be. On the y-axis here, you have your accuracy of the overall model that is trained with FL. On the x-axis is the iterations. If you are not doing any protection in like a typical federated averaging or other methods, as long as there are adversaries injected, this is for training CFAR10, you can see all the accuracy would drop. Essentially nothing is learned because you go at 10%. But with these methods, you can see you can tolerate up to large number of adversaries without a hit on your accuracy. What is the challenge? The challenge is now the quadratic complexity is back. And that's because of the heavy MPC method that you need to run for calculating the distances between the secret shares of the models. Okay, so you can do it, but there is going to be very complicated as the number of users increasing. So again, a question that we don't know its answer is this quadratic barrier here fundamental, or can you break it? Means that in the case of honest but curious, it was shown there are various methods that you can get almost linear complexity. What if you make them Byzantine adversaries? How are you going to solve this problem? We don't know the answer. Another problem here is so far we assumed everything is homogeneous. The models that need to be aggregated, as well as how the compression or quantization is done at each user is the same, and the problem is just aggregating them. An interesting question is how to extend those methods to heterogeneous setting, whether heterogeneous models, users working on different model sizes, or heterogeneous quantization. In those cases, again, the server doesn't know who is giving you a model at a finer scale and who is giving you at a coarser scale. So the question is, how do you aggregate it so you are combining them carefully? We have done some works in that domain on secure aggregation with heterogeneous quantization that you can take a look for some detail. Finally, a third open direction is more of, as you can see, there has been a lot of emphasis on the server to do the aggregation, coordinate between the users, etc. This is motivated by scenarios that, for example, federated learning is driven by cloud companies like Google, Amazon, etc., that they play the role of the server. But at the same time, there are perhaps many applications of federated learning that it is decentralized across many users. Okay, so for example, over an app, you want to enable federated learning for better trading mechanisms over Robinhood users. And there is no server there. This is something grown among the users. So understanding these aspects when there is no server is a very interesting direction. Many of the schemes that I mentioned relies on having a server to help with the process, and how to do it, especially in the presence of Byzantine adversaries, is a future direction that is interesting to pursue. All right, so I'm done with the first part. We have 10 minutes left. As I mentioned to you, I was also planning to tell you a little bit about how to do federated learning for large models. And the third part would be the FedML ecosystem that we have, to tell you a little bit about this research library and benchmarking platform that you may want to use. So maybe a question that I want to ask you is, in the remaining 9 minutes, what do you like to hear? And we take it from there. So the choices are federated learning for large models, like how to use small models, or give an overview of the Federated library in case you want to use our libraries for your federated learning.
So maybe one thing, Salman. So I don't mind if you go a bit over time. So if you wanna, you can cover both if you have time. And anyway, for people who have to leave, we still upload the recording to our YouTube channel so they can catch up later. So I guess like if you have time to stay a bit over time, then you can just go and cover both parts.
Very good. So I don't think we need more than like 5 to 10 minutes to go over.
So I guess that's
let's do
completely
it.
Okay.
And then whoever, I mean, that's the beauty of virtual. At least it has some advantages. Anybody can leave and it would be recorded. All right. So we want to move and discuss a little bit these large model effects. And the key idea is, again, if you talk about, many people talk about federated learning, the starting point is you are assuming that the users can train these large models. But these users are often phones, they are like echo devices that are like less than $100, etc. So good luck training a complicated DNN locally at those nodes. They don't have the sufficient memory, compute power, etc. So a critical problem is how to efficiently train large models over resource-constrained edge devices. And the idea is that you can't even fit the model there to proceed. This is a very important problem. I would say, a lot of opportunities for innovation and making contributions there. Our approach to this problem has been to cast this problem as knowledge transfer, meaning that the typical federated learning is the transfer of models to the server. But these models, you cannot fit them at the device. So now the way we recast the problem is each user can train smaller models. How would I transfer the knowledge from these smaller models to a bigger model at the server? Okay, so if you view it that way, then you don't need to insist on the federated learning to just be the aggregation of the models. It could be the transfer of the knowledge from light clients to the big client. And that's where we had a paper recently called Federated Group Knowledge Transfer that tries to formalize this concept for training large models. And the idea is that essentially you would train smaller models, view them as a smaller feature extractors at the edge nodes, and a large classifier at the server. Okay, but you need to couple these two problems together so that the users can leverage each other to come up with better extractors, and the server can absorb the knowledge from the small users and the features they have extracted, so it can train a better classifier. So the question is, how do you formulate such a problem, right? So at a high level, it makes sense, but you have to formulate it in a federated learning scenario to figure out how to couple the two. So let's start with a naive formulation and we take it from there so that I tell you how we formulated the problem. So in a naive formulation, there is like a small feature extractor and a small classifier at each node. And there is also a big classifier, WS, at the server. What each node, edge node is doing is trying to, okay, so what this messy equation is, each edge node is trying to come up with a feature extractor at classifier that minimizes the loss locally at its own, okay? Then it would provide these, features that it has generated, like intermediate values, HIs to the server. The server is gonna use those features that are extracted by each node and tries to figure out what is the large model that it would minimize its own loss. So in this naive formulation, this is good because each node can use a small feature extractor. And also it is good because the server is getting a lot of information from the clients and can train a bigger model. The problem with it is, as you can see, these models, the light models at the edge nodes, are not getting better because they are not leveraging the data at the other nodes. And if you have limited data at each edge node, essentially you are going to come up with a crappy feature extractor. And that would also affect the server because it's going to put your feature, your bad features or crappy features to train, and the performance at the server won't get boosted. So that's where you want to couple the two together. And the idea is you couple them through a knowledge distillation loss. Okay, so what it would mean is that the server is also gonna provide essentially the logits or the soft labels that it knows that it has learned to the client. So those logits or the soft labels that are learned by the server is like the aggregate of what the server has learned collectively from all the edge nodes. So it would provide to that. Now look at one of the users. That user previously just tried to minimize its own loss over the data that it has. But now it's also going to add a new knowledge distillation loss. What it would mean is it tries to make its feature extractor as close as possible to the server's soft labels. So it's kind of tries to learn from the server on what is a better feature that could be generated. Now, in the same manner, the server is also gonna incorporate more information from the users beyond just the features that they have learned. It tries to make its feature extractor so that it is becoming good for aggregate of all the users. This way, essentially, you are formulating this problem as alternating minimization problem between the server and the edge nodes. The coupling is through the knowledge distillation loss, and they can help each other to boost their performance, meaning that users bring their predictions closer to the model prediction to the server side, and the server would also absorb what they have learned, what each user has learned. So what we have done to show the power of this approach, we have looked at the scenario of training ResNet 56 across all the nodes. In one scenario, you look at the typical federated learning scenario that ResNet 56 is trained at all of the users. In the other setting, we look at our group knowledge transfer setting where this user side model is very small, is tiny ResNet 8. Sorry, 1 second. Let me put it back again. All right, very good. So just to recap, in one side, ResNet 56 everywhere. In the other side, very tiny models using FedGKT for training ResNet 56 only at the server via knowledge transfer from the users. And we have looked at the performance of that for several problems, starting from a simpler CFAR 10 to CFAR 100 and also CNIC 10. What are these plots? You need to pay attention to only blue and red. These are the performance versus iteration, like typical accuracy plots. The important thing is that in all the scenarios, there is no difference between our knowledge transfer method and what you can do, assuming that you can train the big model at each user. What happened? All right, sorry about that. So the blue and red are the same. In fact, sometimes even red is getting better than blue. That's because of the over parameterization that sometimes would happen at each user by training a big model that is not necessary. That's why we have sometimes a slight even improvement over ResNet 56 everywhere. So you are matching the performance, but you are saving tremendously on your flops at each user. For example, this is assuming that you do ResNet 56 at the users compared to ResNet 8. So you are saving about 10x on computing, about 15x on, sorry, about 50x on number of parameters or the model side, as well as about 15x on the runtime at each server. So this shows the potential of matching, like essentially doing large scale training with only small models at the users, which I think is promising, but there are many directions. Again, this is one of the early works that I'm aware of that explores federated deep learning on edge devices, like working on deep models. There are many interesting problems, like theoretically, this is not explored. How small can you make the user's model? Is there a model size versus performance trade-off? Where the ResNet 8 came from, our scenario was we started shrinking until we didn't match the performance, and ResNet 8 was the tipping point. Below that, our GKT method was not performing well. So in general, how small can you make it? I think that's a very interesting problem. Another issue is, in these methods, you have to provide the hidden features to the server to do the model training at the server. These hidden features may leak some privacy guarantees. So how would you do that? Meaning that how would you think about aggregation methodologies beyond just averaging? And finally, these methods would work like FedGKT allows for different models at the users. So far, we fixed the model. We said everybody is doing ResNet 8. I think it's very interesting to figure out what are the right models at the users, or what are the model adaptation and personalization that can happen at each user. We have done some preliminary work here. There is a workshop paper that we had to cast this problem as a federated neural architecture search. But in general, I feel that's a very important problem to think about what are the right models for the clients, not just a generic model that is done to the users. All right, so we come to the almost the end of the talk. In the last couple of minutes, I want to tell you about our open source library and benchmark for federated learning. All the algorithms that I talked about and the experiment I showed you, we have done in FedML. Several of you may be familiar with FedML. So FedML is an open source research library and benchmarking for machine learning. Here is the link. And, we have been, as you all know, there are also other libraries for federated learning, like the TensorFlow Federated by Google, Leaf, PySwift, Fate, etc. All of these libraries are excellent, but our goal has been, to come up with a library that overcomes some of the, shortcomings in the existing libraries. For example, having platform diversity, having system configuration. You want to have not only centralized federated learning, but vertical federated learning, hierarchical federated learning. These are important scenarios that would arise in different contexts. You want to have those topologies. You also want to have a lot of benchmarking and implementations, both on the algorithmic side as well as the data sets. And the libraries that I mentioned to you, for example, if you want to try FedGKT, try the secure aggregation protocols, not many of them have those. Our goal has been to develop a library that has many of those algorithms as well as the benchmarking data sets. So here is like a list of many data sets that we have. And that's why we came up with the FedML library. I won't be able to go to the detail to show you what are the features there. But maybe I tell you about some of the recent releases that we have had in FedML, so that if you are interested, you can explore FedML library. So the community of FedML is growing. We have a lot of Slack users and GitHub contributors that I should thank them for contributing to FedML. It has also been recognized by both industry and academia. And some of the recent things that we have been doing is to develop diverse libraries that are targeted for a wide variety of applications. So a new one that we released just on Monday is FedNLP. This is a complete library for a variety of natural language processing tasks. For example, if you want to look at the problems of text classification, span extraction, sequence tagging, sequence to sequence, language modeling, all of these tasks are already available in FedNLP. There is various data sets with the corresponding heterogeneous partitioning that you can use, as well as various algorithms like FedApp, FedOp, etc., that you can work with these class of problems. The good thing is, once there is a wide variety of tasks, wide variety of algorithms, you can start asking yourself, what are the key problems that could arise in federated learning for natural language processing? And in fact, in this paper that we just posted on Monday to archive, we have highlighted several interesting problems that could arise, and they are specific to NLP application domain. Another library that we have released is FedGraph Neural Network. This is the application of federated learning for graph neural network training. As you all know, graph neural networks are gaining attention. It arises in many scenarios, like in the recommendation system, social networks, finance domain. These are better models as opposed to other DNNs for inference and solving of the problem. We have done collaboration with Tencent AI Lab to come up with a library that has, similar to FedNLP, a variety of tasks, algorithms, and formalizes what would graph neural network training for in a federated setting would mean. Finally, a third library that we have also released is FedCV. This is federated learning for diverse computer vision tasks beyond just the naive, data set and tasks like CFAR10, etc. So we have looked at image classification, image segmentation, object detection for a variety of data sets. And as I mentioned, many of the algorithms that I talked, like FedGKT, FedNAS, the secure aggregation, they are already embedded, available there. So if you're working on any of those application domains, maybe you will find the library, something you want to interact with and use for your research. All right, that's my final slide. As I mentioned to you, federated learning, we all know, is an exciting area. I highlighted several of our works in this domain, but there is so much more that needs to be done. One direction that I highlighted was to understand key problems in different application domains. And that's something that we are exploring to understand the details of what is next for federated learning. Let me stop here.
Thank you, Salman, for your excellent talk. So I think we are a bit over time, but I don't know if you can stay for a bit around. Maybe there will be some questions from audience. So please feel free to either post question to chat or just raise hand. So there's one question from Giovanni.
Hi, thanks for the talk. You touched many interesting topics. There was, at the beginning, exactly in this slide, you mentioned that you also have done some work, if I got understood, on unsupervised federated learning, or semi-supervised. I'm curious if you could say a few words more.
Very good. So that one, we don't have a paper out yet. So we are working on it yet. So there is nothing specific I can mention, but it's more of how would you even formulate, what is the federated? So maybe I mentioned to you some of the challenges. As you know, unsupervised learning, there is a lot of exciting developments there based on contrastive models, etc., for leveraging those for the training. The issue means you can start looking at it in federated setting. The problem with it is the amount of resources you would need to go from supervised to unsupervised is going to become more. Meaning typically the number of iterations is going to be much more. The amount of data you would need is going to become much more. And that's where the challenge is, it's pushing you to the opposite direction. So the one direction that we have been exploring is how to do efficient unsupervised FL. Means that you don't want to just bring it, the setting to the federated scenario because it will blow up your resources. So that's the direction that we have been pushing.
Okay.
But at a high level, I mean, you can imagine, you can apply, you can generate similar images at each user, correct? That's the typical method. For example, you do various rotations, various transformation, and you try to train contrastive models that tag them as similar, or if they are different, tag them as different, right? And then the question is, what would I aggregate across different users? Would it be good to average these contrastive models or not? These are the questions that we are exploring.
Definitely, it's an interesting topic. I mean, I will look forward to see your paper appearing online.
Thanks, you. Definitely.
So then there is another question by Konstantin.
Thank you for the talk. I have a couple of questions. One question is about piecewise models, like gradient boosting decision trees, random forest, etc. So they have, like, from statistical learning community, so they have nice built-in features, like fixed missing values, handle categorical variables. And I'm curious, do people, so there are modern things like graph neural networks, pointwise neural networks, etc. But do people care about have in federated learning setting models like decision trees?
Excellent question. That is true, meaning maybe if you view federated learning, you see, one way is to view federated learning as you want to train a deep model, right? In that, if you view it that way, then there is no room for other models. You have to use a state-of-the-art big models, correct? But there is another view that you view federated learning, that there is like a data analytics problem that you want to solve. For example, that data analytics is you want to, for example, look at conversational AI. For example, if a user says one sentence, what should be the next sentence in response? Then in those cases, maybe what you want to train is a simpler scenario. Like, for example, you want to know a knowledge graph, you want to build a decision tree, etc., right? So meaning not all the problems require complex models, and federated learning could be applied to those problems too. Especially this would arise as if you are optimizing something at the users. For example, you don't need complicated model. Maybe you want to think about, what should this user do tomorrow? What are the recommended, set of actions based on the past history? Arguably, you don't need a complex model for that. And that's where FL can be useful. I hope that answers your question.
Okay, yeah, thank you. Yeah, a second question about, in the slides, it was mentioning about NAS for federated learning. Can you comment on this? Because we first,
which slide was it, sorry?
I think it was maybe 5 slides ago. Okay, you can scroll and I will back.
Oh, the masterless, the serverless one, right?
Here, this one. The next slide. The next. This one, FedNAS, Federated Deep Learning with Neural Architecture Search. So can you please comment? So this is a joint optimization strategy for finding parameters and model. So
that's right. So let me explain a little bit here. So you see, typically data heterogeneity in federated learning is addressed at the algorithmic layer, correct? The idea that we have pursued here is that how to address data heterogeneity by tuning the model at each user. Okay, so meaning that maybe because of data heterogeneity, different users need different models. And that's why we cast it as a neural architecture search. But to do it is essentially think about, for example, various operations that the user may do for connecting, tensors together. The question is how to choose those connections. You have to come up with a loss function and that captures those different architectures and use federated learning for optimizing that architecture at the user. That's the approach that we have taken.
I see.
Okay, so it's kind of you're defining a loss that captures different architectures that you want to do. The way that you can do it is, you want to make sure this loss is differentiable, right? So the way you would do it for each choice, of course, is binary, whether you use this pooling or you don't use that. You have to model it as like a typical, soft thresholding so that you can take the differentiation and define a loss based on that. But take a look at the paper, is available on arXiv.